Welcome back, everyone. Ready to dive into another fascinating corner of astrophysics?
Absolutely. Always eager to explore the mysteries the universe throws our way.
Well, today we're taking a deep dive into neutron star and black hole mergers.
Ah, yes. Those cataclysmic events where gravity reigns supreme.
Exactly. And you've given me some really in-depth research on this. We're going to be focusing specifically on the role of neutrinos in these mergers.
Neutrinos, tiny particles, but they pack a punch, especially in these extreme environments.
So before we get lost in the quantum world, maybe we can set the stage a bit. I mean, we're talking about objects so dense that a teaspoon of their matter would outweigh Mount Everest.
That's right. Neutron stars and black holes are the remnants of massive stars that have collapsed under their own gravity. When a star runs out of fuel, it can no longer support itself against this inward pull, and the core implodes.
And depending on the initial mass of the star, this collapse results in either a neutron star or a black hole, right?
Precisely. A neutron star is essentially a giant atomic nucleus, composed mostly of neutrons packed incredibly tightly together. Imagine squeezing a star several times the mass of our sun into a sphere with a radius of just 10 kilometers.
Wow, that's mind-bogglingly dense. And a black hole is even more extreme.
Indeed. It's a region of spacetime where gravity is so strong that nothing, not even light, can escape. It's like a cosmic trapdoor.
And these objects, neutron stars and black holes, can actually collide with each other.
Yes, they can, if they happen to be in a binary system orbiting each other. Over vast stretches of time, they lose energy through the emission of gravitational waves. This causes their orbit to shrink until they eventually merge.
So it's a slow dance of death, culminating in this incredibly violent collision.
You could say that. And these mergers are some of the most energetic events in the universe,
Yeah.
releasing an incredible amount of energy in the form of gravitational waves, electromagnetic radiation, and of course, neutrinos.
And these events are pretty rare, right?
Extremely rare. We've only observed a handful of them directly so far, but each observation is a treasure trove of information, giving us a glimpse into the fundamental physics of matter at extreme densities.
Speaking of treasure, one of the key areas of research surrounding these mergers is the creation of heavy elements, right? Like gold and platinum.
Exactly. Elements heavier than iron, like those precious metals you mentioned, are primarily synthesized through a process called the R process, which stands for rapid neutron capture. This process requires extremely neutron-rich environments, and the ejecta from neutron star mergers seem to be a prime location.
So these collisions aren't just about mind-boggling densities and gravity, they're also cosmic forges, creating some of the elements that make up our world.
Precisely. And to understand how this element creation process unfolds, we need to delve into the anatomy of a neutron star merger.
Okay, let's break it down. What actually happens when two neutron stars collide?
Well, it's a very complex and rapid process happening on timescales of milliseconds. As the two stars approach each other, their immense gravity begins to distort their shapes.
So they're no longer perfect spheres.
Right, they become more like elongated ellipsoids, and as they get closer, tidal forces begin to rip material off the less massive star.
It sounds chaotic.
Yeah.
So one star gets cannibalized by the other.
In a way, yes. This material forms a spiraling disk of superheated gas and dust around the more massive star, or the merger remnant if the two stars have already coalesced.
And this disk is where a lot of the heavy element creation action happens.
It's one of the key locations. You have this incredibly hot and dense environment with lots of neutrons flying around, which are essential for the FAR process.
But not all the material ends up in the disk, right?
Correct. Some of it gets flung outwards at incredible speeds, forming what we call dynamical ejecta. This material can escape the gravitational pull of the merger remnant and eventually seed the interstellar medium with heavy elements.
So we have this interplay of material spiraling inwards to form the disk and material being ejected outwards. And within this chaotic environment, heavy elements are being forged.
Exactly. And to really understand how this happens, we need to talk about a crucial concept: the electron fraction, often denoted as Ye. This essentially measures the relative number of protons to neutrons in the material.
Okay, so a high electron fraction means more protons, and a low electron fraction means more neutrons. And for the R process, we need those neutrons.
Exactly. The lower the electron fraction, the more neutron-rich the environment, and the more favorable the conditions are for the R process to occur.
So how do we know that those conditions are actually met in neutron star mergers? How do we measure this electron fraction in the material that gets ejected?
That's where kilonovae come in. These are the electromagnetic counterparts to the gravitational waves emitted during the merger. They are powered by the radioactive decay of those heavy elements we were just talking about.
So the kilonova is like a cosmic fingerprint, revealing the composition of the material.
Precisely. The color and evolution of the kilonova light curve, the way its brightness changes over time, are directly related to the electron fraction. And that tells us something about the elements being produced.
So by studying these kilonova signals, we can start to piece together the puzzle of heavy element creation in these incredible events.
Exactly. But there's another piece of the puzzle that plays a crucial role in shaping the aftermath of these mergers. Neutrinos.
But let's talk about neutrinos. These are those elusive particles that are notoriously difficult to detect, right?
They are. Neutrinos interact very weakly with matter. They can pass through vast amounts of material, including entire planets, without being affected.
They're also incredibly abundant in the universe, right?
Yes, they're produced in vast quantities in nuclear reactions, like those happening in the sun and other stars. And in the extreme environments of neutron star mergers, they play a surprisingly significant role.
So how do neutrinos actually interact with matter in these collisions? What are the main processes at play?
Well, there are several key processes. One is charged current reactions, where a neutrino interacts with a neutron or a proton, essentially swapping identities and changing the overall neutron to proton ratio.
And that directly affects the electron fraction, which, as you said, is crucial for the R process.
Precisely. Another important process is pair production and annihilation, where pairs of neutrinos and antineutrinos are created and destroyed. This can contribute to the overall energy balance of the system and maybe even power those relativistic jets we see in some mergers.
And then there's scattering, where neutrinos bounce off other particles, influencing their trajectories and how they transport energy.
And on top of all that, there's this fascinating phenomenon called collective flavor oscillations. This is where neutrinos can actually change their flavor or type as they travel through the dense material.
Wait, so neutrinos can change their identity mid-flight?
Yes, it's a consequence of quantum mechanics. Neutrinos exist as superpositions of different mass states, and those mass states evolve differently over time, leading to these oscillations.
Wow. So we have all these complex neutrino processes happening, these collisions, and it's all influencing the evolution of the merger remnant, the composition of the ejected material, and ultimately the creation of heavy elements.
Exactly. And to fully understand the R process and the abundance of elements we observe in the universe, we need to unravel the intricate ways these neutrinos shape the aftermath of neutron star mergers.
This is all incredibly fascinating, but it also sounds incredibly complex. How do we even begin to model these processes and make sense of the observations?
It's a challenging task, but we are making progress. By combining sophisticated numerical simulations with detailed observations of kilonovae and other electromagnetic signals, we're starting to piece together the puzzle.
And the more we learn about these collisions, the more we learn about the fundamental workings of the universe, from the behavior of matter at extreme densities to the creation of the elements that make up our world.
It's a journey into the heart of some of the most extreme environments in the cosmos, and we're just at the beginning.
This has been an incredible overview. Thank you so much.
Welcome back to our deep dive into neutron star and black hole mergers.
Where we're really starting to see just how important these tiny neutrinos are.
Absolutely. Last time we talked about what neutron stars and black holes are, how they collide, and hinted at the crucial role neutrinos play.
Yeah, and we even touched on the R process, which is responsible for making all those heavy elements like gold and platinum.
Right, and we talked about kilonovae, those bright afterglows, which give us a glimpse into what's going on in the material ejected during these mergers.
And you mentioned that neutrinos can actually change the composition of this material as it gets blasted out, which ultimately affects which elements get produced.
Exactly. And that's what we'll be focusing on today. We're going to take a closer look at how specific neutrino interactions change the electron fraction and therefore the nucleosynthesis pathways.
Okay, so let's start with those charged current reactions.
Yeah.
They're like the main players when it comes to changing the balance between neutrons and protons, right?
That's right. The electron fraction, or Y, tells us the relative number of protons compared to neutrons.
And we know that different E values lead to different R process outcomes, ultimately affecting the final abundance of heavy elements.
Precisely. So in a neutron star, which is already incredibly neutron-rich, these charged current reactions have a crucial role to play.
Okay, so let's imagine we have a neutron deep inside a neutron star. What happens to it?
Well, it's surrounded by a sea of other neutrons and a smaller number of protons and electrons. One of the key charged current reactions is where an electron neutrino comes along and interacts with that neutron, converting it into a proton and an electron.
So it's like the neutrino is swapping identities with the particles it encounters.
In a way, yes. This reaction increases the number of protons, decreases the number of neutrons, and ultimately increases the electron fraction.
Ah, so it's making the material less neutron-rich. But what about the opposite? Can an electron antineutrino interact with a proton, turning it back into a neutron and a positron?
Absolutely, that reaction also happens, and it works to decrease the electron fraction. The balance between these two competing reactions determines how the yi of the material evolves.
So it's like a tug of war, with neutrinos and antineutrinos pulling in opposite directions, and the neutrons and protons stuck in the middle.
A very good analogy, but we also have to consider the environment. The inside of a neutron star is unlike anything we can create in a lab.
Right, it's incredibly dense and hot.
Exactly. And the rates of these reactions are highly sensitive to the temperature and density of the material. In the core of a neutron star, where densities and temperatures are extreme, neutrinos are essentially trapped.
Trapped? How can something so small get stuck in something so massive?
It's because of the sheer density of particles in the core. Neutrinos are constantly interacting with other particles, being absorbed and re-emitted so often that they can't travel very far. It's like trying to move through a crowded room.
I can imagine. But they do eventually escape.
Right. Yes. As you move outward, away from the dense core, both the temperature and density decrease. Eventually, you reach a point where neutrinos can escape. We call this the neutrino decoupling surface.
So there's a boundary where neutrinos go from being trapped to being able to stream freely away.
Precisely. And the location of this boundary is different for different types of neutrinos. Electron neutrinos, which interact more strongly with neutrons, decouple closer to the surface of the neutron star, where the temperatures are lower.
So they can make a faster getaway.
You could say that. Electron antineutrinos decouple a bit deeper in at slightly higher temperatures. And then you have the heavy lepton neutrinos, muon and tau neutrinos, which interact much less strongly with matter.
So they just zip right out.
Not entirely. They decouple at even higher densities and temperatures than electron neutrinos and antineutrinos, but they can still experience scattering events, making their journey out a bit more roundabout.
Okay, so we have this complex interplay of reactions and decoupling surfaces, all shaping the neutrino outflow from a neutron star. But how does this affect the material that gets ejected during a merger?
That's where things get really interesting. Remember those different ejection channels we talked about? The cold tidal ejecta, flung out during the initial disruption of the neutron star, doesn't interact much with neutrinos.
So it keeps its low electron fraction, stays very neutron-rich.
Exactly. But the hot material ejected from the disk or the neutron star remnant, as well as the material from the collision interface, those experience significant neutrino irradiation, pushing their electron fractions to higher values.
And that explains why we see such a variety in the composition of the ejecta and ultimately in the elements that get forged in the process.
Precisely. The range of electron fractions shaped by neutrino interactions leads to a diverse mix of heavy elements, reflecting the complex dynamics of these collisions.
Okay, so we've covered the charged current reactions in detail. What about those other neutrino processes we mentioned earlier? Do they have a significant impact on the merger aftermath?
They certainly contribute, though their effects might be more subtle compared to the direct impact of charged current reactions on the electron fraction.
Let's start with pair production and annihilation. Remind us what those are all about.
So in pair production, you have energy, often from interactions between electrons and positrons, converting into a neutrino and an antineutrino pair. This can happen for any flavor of neutrino, though the specific rates vary.
And this is how we get those heavy lepton neutrinos, the muon and tau neutrinos, in the mix.
It's one of the primary mechanisms, especially since charged current reactions involving muons and TAS are less common in most parts of the merger remnant.
Makes sense. Now, what about pair annihilation?
In this process, a neutrino and an antineutrino collide and annihilate each other, releasing energy. This energy can then go into creating other particles, like electron-positron pairs.
And this is the process that might be involved in powering those short gamma ray bursts, right?
Yeah.
Those incredibly powerful bursts of energy we sometimes see from these mergers.
It's one of the leading possibilities. We know that neutrino pair annihilation can deposit significant energy in the polar regions above the merger remnant.
Why The polar regions specifically.
Because that's where you have neutrinos coming from different parts of the system, the disk, the neutron star remnant converging. This increases the likelihood of those neutrino-antineutrino collisions.
So it's like a cosmic intersection where neutrinos from all directions are meeting up and some of them decide to go out with a bang.
A very vivid description. And this energy deposition can have important consequences. It can heat up the material in the polar regions, potentially contributing to the formation of outflows and jets. It can also accelerate particles to incredibly high speeds, influencing the overall dynamics of the system.
Okay, so we've got pair production and annihilation, adding another layer of complexity to the neutrino story. What about scattering? How does that factor in?
Scattering is when a neutrino bounces off another particle, like a neutron, proton, or electron. These interactions don't directly change the electron fraction like charged current reactions do, but they influence how easily neutrinos can travel through the dense material and how much energy they lose or gain along the way.
So it's more about directing traffic than changing the composition of the material.
You could think of it that way. Scattering can affect the overall transport of neutrinos, determining where they can escape from, how quickly they cool certain regions, and how their energy gets redistributed within the system.
So it's like scattering is setting the stage for the other neutrino processes to play out.
Exactly. And all of these processes are intertwined, creating a complex web of interactions that shape the evolution of the merger remnant and the composition of the ejecta.
And it's this intricate dance of neutrinos that ultimately determines which elements get forged in these cosmic collisions.
Precisely. The variety of neutrino interactions, influenced by the extreme temperatures and densities, leads to a diverse range of electron fractions in the ejected material.
Which, in turn, drives the R process down different pathways, producing the incredible array of heavy elements we observe in the universe.
And by studying the light from kilonovae, those explosive afterglows, we're getting a glimpse into this intricate process, piecing together the puzzle of element creation.
Okay, we've covered a lot of ground here, delving into the specifics of neutrino interactions and their role in shaping the aftermath of neutron-star mergers. But there's one more piece of the puzzle we need to discuss: those collective flavor oscillations.
Ah, yes. The quantum weirdness of neutrinos taking center stage.
Exactly. We briefly mentioned it earlier, but now let's dive into the details. Remind us what these flavor oscillations are all about.
So neutrinos come in three flavors: electron, muon, and tau. And here's where it gets strange. These flavors aren't fixed. Neutrinos can actually oscillate between them as they travel.
They can change their identity mid-flight. That's mind-boggling.
It is. It's a consequence of quantum mechanics. Neutrinos exist as superpositions of different mass states, and those mass states evolve differently over time, leading to these oscillations.
Okay, I'm trying to wrap my head around that. But how did these oscillations play out in the extreme environment of a neutron-star merger?
Well, in these dense and turbulent conditions, things get even more complicated. Individual neutrino oscillations get amplified and synchronized due to interactions with other neutrinos. We call this collective flavor oscillations.
So it's like they're all doing a synchronized dance routine, but a very complex one.
A very chaotic and energetic dance routine. And the choreography of this dance can significantly impact the overall flavor composition of the neutrino outflow.
So that means the relative numbers of electron, muon, and tau neutrinos escaping from the system.
Exactly. And remember, different flavors of neutrinos have different interaction probabilities with matter. So these collective oscillations can influence things like the cooling rate of the merger remnant, the heating of the ejected material, and even the electron fraction itself.
Wow, so it's like another layer of control, fine-tuning the output of these already complex collisions.
In a way, yes. Collective flavor oscillations introduce a degree of uncertainty into our models, but they also offer a fascinating opportunity to probe the fundamental properties of neutrinos.
Because by studying how these oscillations manifest in the signals we observe from neutron-star mergers, we can learn more about the neutrino mass hierarchy, mixing angles, and other parameters that govern their behavior.
Precisely. It's like having a cosmic laboratory where we can test our understanding of neutrino physics under the most extreme conditions imaginable.
Okay, so we've added yet another layer of complexity to our picture of neutrino interactions in neutron-star mergers. These tiny particles aren't just bystanders, they're active participants, shaping the evolution of these events in ways we're only beginning to understand.
And their influence extends beyond the immediate aftermath of the collision. The changes they induce in the electron fraction of the ejecta have lasting consequences, determining the final abundance of heavy elements that get dispersed throughout the universe.
So next time I look at a gold ring, I'll remember those busy little neutrinos working behind the scenes, orchestrating the cosmic alchemy that forged those precious metals.
It's a reminder that even the smallest particles can play a profound role in shaping the universe we inhabit, driving the evolution of stars, galaxies, and even the elements that make up our own bodies.
And we're back for the final part of our deep dive into neutron-star mergers.
Where we'll be zooming out a bit to see how all those intricate neutrino interactions we've been discussing actually manifest in the observations.
Exactly. We're talking kilonovae, those spectacular afterglows that light up the sky after these mergers. We've mentioned them a few times already, but now let's really dig into how those light curves, the way the brightness changes over time, are shaped by the neutrino physics we've been exploring.
Kilonovae are powered by the radioactive decay of all those heavy elements created in the R process. But it's not just the amount of those elements that matters. It's also their distribution, their velocity, and importantly, the opacity of the material.
Right, you've mentioned opacity before. Could you remind us what that means in this context?
Sure, opacity basically refers to how easily light can escape from that expanding cloud of debris created by the merger.
So it's a measure of how transparent the material is.
Exactly. And this is where neutrinos have a subtle but significant influence. Remember how neutrino interactions can change the electron fraction of the ejected material? Well, that directly impacts the types of elements produced. And some of those elements, particularly the lanthanides and actinides, are very good at absorbing light.
Ah, so they're like a cosmic curtain, blocking the light from getting out.
That's a great analogy. And the higher the electron fraction, the more of these lanthanides and actinides you tend to get, which leads to higher opacity in the ejecta.
Okay, so how does this actually affect the kilonova light curves? What would we actually observe?
Well, if you have a kilonova with low opacity, meaning the ejecta is pretty transparent, the light curve will rise quickly, peak brightly in optical and ultraviolet wavelengths, and then fade relatively fast.
So we get this bright flash because the light can escape easily.
Precisely. But if you have high opacity, with lots of those light-absorbing elements in the mix, things change quite a bit.
So the light gets trapped, and we see a dimmer, longer-lasting signal.
Exactly. The kilonova will rise more slowly, peak at later times, and the peak will be shifted towards longer, redder wavelengths because those can penetrate the opaque material more easily.
So it's like the opacity is acting as a filter, both dimming and reddening the light.
That's a great way to put it. And this effect is directly connected to those neutrino interactions we've been discussing. Those charged current reactions that change the electron fraction ultimately set the stage for these differences in kilonova light curves.
So by carefully studying those light curves, we can actually learn something about the neutrino processes that happened deep inside the merger remnant.
Exactly. It's like we're piecing together clues from the light to understand what those neutrinos were up to.
And the more kilonovae we observe, the more data we have to test our models and refine our understanding of this complex interplay between nuclear physics, gravity, and neutrinos.
Absolutely. It's a rapidly evolving field, and each new observation brings us closer to unlocking the secrets of these incredible events.
Now, besides shaping kilonova light curves, are there any other observable consequences of these neutrino interactions?
There are. Remember how neutrino parannihilation can deposit energy above the merger remnant, specifically in the polar regions?
Right, like that cosmic intersection where neutrinos collide.
Exactly. Well, that energy can potentially power jets of material blasting outwards.
And those jets are thought to be connected to some of the most powerful explosions in the universe. Short gamma-ray bursts, right?
That's right. These bursts are incredibly energetic, releasing a tremendous amount of energy in just a few seconds. And while the exact mechanisms behind them are still being debated, neutrino annihilation is a leading contender for providing that energy.
So if we see a short gamma-ray burst along with a kilonova,
Ah,
that's strong evidence that neutrinos are powering those jets.
it would certainly support that idea. And the properties of the gamma ray burst, things like its duration, energy, and even its direction, can give us further clues about the neutrino physics involved.
It's like having multiple windows into the same event, each revealing a different piece of the story.
Precisely. By combining observations across the electromagnetic spectrum, from radio waves to gamma rays, we can build a more complete picture of what's happening in these mergers.
It's amazing to think that these tiny particles, neutrinos, are playing such a crucial role in shaping the universe.
It really highlights the interconnectedness of physics, where the smallest scales can influence the largest, and where seemingly insignificant interactions can drive the most dramatic events.
Well, thank you so much for taking us on this incredible journey through the world of neutron star mergers and the fascinating role of neutrinos. It's been
Mm.
an eye-opening experience.
It's been my pleasure. And to our listeners, thank you for joining us on this deep dive. We hope you've gained a new appreciation for these tiny particles that are shaping the universe in profound ways. Until next time, keep exploring, keep questioning, and keep looking up at the wonders of the cosmos.